So just to recap again, where are we? We started out with this problem. How many colors do we need to color the regions of a map? We changed the problem by looking at the dual graph. That means that we took every face of our map and we turned it into a vertex. And then the edges of the dual graph correspond to pairs of faces that share, or that abut, that share an edge. They share a border. So then we turned the map of the Western United States into this planar graph. And whenever we take the dual of a map, we always get a planar graph. So our revised problem that's more mathematical is what's the chromatic number of a planar graph? And we've come up with a bound so far. We know that for a planar graph, we could need 4 colors, right? K4 is 4 colorable. The Western United States is 4 colorable. So we know that we might need 4 colors. But we proved a theorem last time that says actually 6 colors suffices. So that we can think of as the 6 color theorem. And the crux of our argument there came down to this really powerful lemma that says that in a planar graph, we always have a vertex v that has degree at most 5. And the question is, can we be a little more clever and maybe rule out 6? Maybe 5 colors is enough. And in fact, 5 colors is enough. And let's see why. So here is the theorem that we're going to prove now, the 5 color theorem, which states that every planar graph is 5 colorable. So we need no more than 5 colors. We don't actually need 6 colors. In particular, what that means is this situation will never be forced on us. V will always have among its neighbors at least 2 that are the same color. Let's see why that is. What we're going to do is follow the same proof strategy that we did for the 6 color theorem. We're going to, in particular, go by induction on n, which is the number of vertices of our graph G. Okay, our base case, same as before, n equal 1, which of course we could take to be n up to 5. This is definitely 5 colorable. If you have at most as many vertices as you have colors, you can make all the vertices a distinct color, and then it's properly colored. So our base case is great. Inductive hypothesis, the same as before. We're going to assume that any planar graph with fewer vertices is, with less than or equal to n vertices is 5 colorable. All right, so now let's jump to it. How are we going to prove that 5 colors is enough? Well, if some vertex, say W, has the degree of W less than or equal to 4, then we're going to use the same argument as before. So what do I mean by that? We're going to use the inductive hypothesis. So inductive hypothesis implies that G minus W is 5 colorable. And W's neighbors use less than or equal to 4 colors. So we're done. Just take the 5th color and color W. Okay, otherwise, so that's if we have a small degree vertex. So otherwise, by the lemma, that same lemma that we used before that's written up here at the top, by the lemma, maybe I'll keep it here, there exists a vertex V such that the degree of V is equal to 5. Okay, that means that we're exactly in this situation here. We have a vertex of degree 5. Okay, so let's do some cases. So case 1, if 2 or more neighbors of V are the same color, the same argument works. So I'm not going to write it again, but if 2 of these are the same color, so if this is purple, then that means that, well, this color here, which is orange, is available for V. So we're done. We can just, again, by induction, properly color the graph with this vertex gone, and we have a color left over to color on that when we're back. So now we need to assume that that isn't the case. So now we're going to assume, let's put it over here, that V has, so now assume, so V has 5 neighbors all colored differently. So what we've done is we 5-colored G minus V, right? So we took V out and we 5-colored it, the graph. And now we put V back in and we realize, oh no, all of V's neighbors have different colors. How do we resolve this? Well, what we're going to do is think about the following. So if, and now I'm going to number, it's important that I number these in a circle. So it doesn't matter that I went clockwise instead of counterclockwise, but I want 1 to be adjacent to 2 and 5, okay? So we want to look at the bipartite graph of just purple and green vertices. So if the bipartite graph, remember bipartite means 2 colors, if the bipartite subgraph of, and maybe we'll steal these guys. So let's duplicate them out. I'm probably going to want lots of these, so we'll just keep going. So if the bipartite subgraph of purple and green connects, or rather does not connect, W1 and W3, then reverse the colors on the component of W1. And then we're done. So what does that mean? That means that if I'm looking at this subgraph and say, okay, W1 goes over to here, and maybe we'll take W3 is maybe connecting to these guys. So suppose we have, let's do it this way, maybe some dotted lines. So suppose W1 connects over here to this guy, connects down to this guy, and W3 connects over here and connects over here. Okay, and suppose these aren't connected in any way. Not in a bipartite way, right? So we cannot get from W1 to W3 following just green and purple edge vertices. Then what does that mean? That means that on this component, I could just toggle all the purple for green and green for purple. And then the end result is W1 will be green. And that's fantastic because now we're in this situation of case 1. So we've resolved it. And let's just point out that there was nothing super special about W1 and W2. I'm sorry, about W1 and W3. But now we're going to have to assume that they're like this, right? That they're actually connected in this way. But we could also do the same thing with, let's see, let's duplicate this guy, and we'll duplicate this guy. So for W2 and W4, the same argument holds. So let's get a couple more of those vertices. Let's duplicate them again. And then we'll put here, this guy, and this guy, and then, maybe throw this guy here. And okay, so for W2, okay, it's got some component that's going to be orange and blue. And then W4 is on some orange and blue component. Again, I'm just looking at these bipartite components. And if those two are not connected, then I'm also fine. So let's put our pen back to good use. So same for W2 and W4, which would be this color component. Okay, so if these guys, if we look at this bipartite component, and it's not connected, then we can switch the colors there. But what happens if neither of these, then G is not planar. Why not? Because look, I've got to connect here. And now I've just crossed this edge. This is the not planar part. So the problem is that if I have a path from W1 to W3 that uses only the green and the purple, then it has to go around W2. And then if I take W2 and connect it to W4, it's got to go around W3. So if we just look here, that means that I've got a circle I formed here, and W2 is inside, and W4 is outside. So that means I have to cross the edge at some point because I don't have a common vertex because they're different colors. So that would mean that G is not planar. That, of course, is a contradiction. And that is how we prove the 5-color theorem. And so the question is, okay, can we prove the 4-color theorem? And the answer is yes. That was actually proved in 1976. And it required an inordinate amount of work and a computer. They reduced the problem to a finite number of graphs to check, but that finite number was so enormous that a computer had to do the check. Now, that proof's been refined a few times, once in the 90s and again in 2005. And the proof's now a little more elegant, but it's still a great example of computer-assisted proofs in mathematics, which is a whole area in and of itself. Automated proofs and computer-assisted proofs are a fascinating thing that a lot of people are doing research on just as a topic in and of themselves. And the four-color theorem is maybe the first and maybe the greatest example of using that. But for us, we'll stop here. You definitely don't need more than 5 colors, and you'll just have to take it on faith or go read the paper to see that 4 colors is actually plenty.